problem is basically you're given a bipartite graph. A bipartite graph is a graph where you have two sets of nodes such that no node is connected to each other within the set. So, for example, something like this would be a bipartite graph. As you can see, this over here is one set and this is another set, and there is no node within this set that is connected to any other set. So, for example, if we had an edge over here, this would no longer be a bipartite. This would no longer be a bipartite graph with these two being the sets. I am not 100% sure if there's some combination of sets that would allow it to be a bipartite graph, but I'm assuming no. Now, the question that we're trying to answer is that with this situation, is it possible for each node in this set to be matched up with a node in this set? From this example, I'm pretty sure we could find a matching that works. So, for example, if we match this to this person, if we match this person to this person, oh, never mind, it is impossible because these two nodes have only one connection, and that is to this person. So it's impossible for both of them to be with this person. So we have a love triangle going on. All right, I think if we have another edge over here, then everything works out. Yeah, then everything works out. So this person could be with this person could be with this person could be with this person, and this person could be with this person, and you would have a matching. Now, let's say we just want to have an algorithm that allows us to figure out if such a matching exists. As we've seen, such a matching does not always exist. One thing that we could do is we could treat this as a max flow graph, right? We could have our starting edge over here. All right, so there are plenty of videos on YouTube for what a max flow graph is, but I guess I'll go over it over here as well. So in a max flow graph, you have a starting edge and you have a terminating edge, right? And you have a starting node and ending node, and you have nodes in between. These in between and each of these edges has some weight, something like that, right? And let me just yes, and just to make it a bit more complicated, and what max flow asks is, imagine these are pipes, and this is the capacity of the pipes, like how much water can flow within the pipes. What max flow asks is how much, if we're using the pipe or water analogy, would be how much water could flow from this to this, right? And there are algorithms to be able to solve it. That would be an entire video on its own, but that's just to give you a rough idea of what a max flow is. So we could have one flow going over there, and that would go through the 40. So that would have it so that we currently have a flow of 1. Then we could have a flow going from the 20 going down here, going through there, that would give us a flow of 11. This edge would be fully saturated, this will be fully saturated, and this is not yet saturated, right? And not all edges are going to be saturated. And then you could also have a flow going this way, right, from the 20 to the 3, and this would make it so that we took 13 out of here, so this would have 7 left, this would have 0 left, and this would have 0 left, and this would have 0 left, and 11 flow is going to be flowing through there, so it would end up having 29 flow left, right? And in total we would have a flow of 14 from the start edge to the final edge. And another thing that we can notice is this max flow corresponds to a min cut where all these edges are 0. And if we were to add up all of these edges, right, so 10 plus 1 plus 3, that gives us 14, which was our maximum flow. So our maximum flow corresponds to a min cut, where the min cut is defined as a set of edges that breaks the graph into 2 different parts such that that set of edges is as small as possible, and usually I think your start edge is in one set and your terminating node is in the other set. Not the best definition, but first video, so bear with me. Alright, so given that, how can we use all of that information in order to figure out if a pairing is possible? So that's our start edge, and that is our sink or terminal edge. And what we do is we combine it in this way. Ta-da! Right, now all of these edges you can think of as having a capacity of 1. Right, and basically, if when we run our max flow algorithm on this, it tells us that it's going to give us the max flow, and depending on what the max flow is, we can figure out if such a pairing is possible. For this particular graph, if the max flow ends up being 4, it can't be greater than 4 because we have one cut over here and one cut over here, both of which would mean that, so the min cut we know is min cut, oh shoot, yeah, so we know that the min cut is at most 4, therefore the flow through the entire graph is at most 4. Now it all depends on here whether there is a way to, it all depends on here whether there is a way for a matching such that that it allows for a max flow of 4. So what we were able to do is take this problem of max flow, right, the algorithms for this, and we're able to use them in order to solve the problem of bipartite matching. Now, this bipartite matching problem only has the constraint that one person from this set can only be with one person from this other set. However, what this problem does is it introduces some more constraints that we have to take into account. In this problem, the constraint of one person only being able to be with one other person, they are they are made through these edge weights, right? So for example, if this was 2, this would mean that this person can be with 2 people from over here, and that would mess up our max flow method in order for figuring this out. All right, so we're gonna be looking at some other max flow things. So let's say you have our start edge, you have some okay, maybe something like this. Let's say that this edge weight is 10, 5, 7. They're arbitrary, no need to stress about it too much. And these both lead into the terminal edge. Now, not too bad of a graph, but let's say we wanna have another constraint that a node can only have a certain amount of stuff flowing through it. How would we be able to reduce this problem where not only do the edges have a capacity, but the nodes also have a capacity, into a max flow problem where only the edges have a capacity, right? A problem that we are familiar with. And the answer is quite, well, I don't know if it's simple. The answer is simple once you get to know it, but I don't know how simple it would be for you to come up with it on your own. What you can do is break a node down into 2 different nodes and have an edge connecting between them, and whatever the capacity of the node was, you give that capacity to the edge. And this second node, the one that we created, we will use this to connect to all of the nodes that our original node with some capacity was originally connected to. And what this effectively does is, now this entire system acts as a single node with a capacity of 5 because it can't have a flow of greater than 5 through it, constrained by that edge. Now, that is just one trick that you can do with max flow. Let's see, there's some other stuff that we can do with max flow. And again, we're building up to what the heck is going on here. So, what else can be done with max flow? I'll use the back of the notebook, though I rarely ever do. We'll start with the previous question that was asked on this exam. I hope this doesn't have any copyright on it. Okay, after this I gotta make sure that the exam doesn't have any copyright on it, but let's not use it. Right. The question that we're given is, we have some students in a pet shelter, and we also have some pets. The students are compatible with certain pets. This line over here indicates compatibility. constraint that we're given is that the students would like to meet some amount of bets. We can match this constraint by simply having an edge that contains their capacity. And we're also told that the bets can only meet, and the bets also have a certain, have a maximum of the number of students that they can meet. Afterwards, I assume they just get tired. And we'll have our start node here, and we'll have our terminal node here. Now, yeah, this graph can be simplified by having these edge weights be directly over there, but I've drawn it, now I'm too lazy to fix it. So we're just gonna assume that these have an edge weight of practically infinity. And again, these all have an edge weight of 1. Right. And this basically solves the problem of students, and when we run the max flow on it, we have to make sure that our max flow is equal to S4 plus S3 plus S2 plus S1. Because if it is not, then that means not all of the students were able to meet up with as many pets as they would have liked. And we also have a restriction on the pets now. So over here, students are matching up with multiple pets, and let's now, with this restriction, we make it so that this pet doesn't meet with more than that many people, because each connection over here represents a meeting, and as long as this edge weight is less than P1, as long as the flow going through here is less than P1, that means this pet has not had more than its maximum meeting, so it hasn't been tired. Now with the S, we don't have to just make sure, so this acts as a constraint, right? While for all this is more like a criteria that has to be met, right? This is like an upper bound, this is like an equal sign, so all of these have to be fully saturated in order for this problem to work. You can think of like as a min cut going through here, and we have to make sure that the min cut is through here and not through there, though I don't think that is too useful of a tool, so my apologies. All right, now that's relatively simple to do, right? Now on to something more complicated, because we can do a lot more with this. Now, let's say we also want to add a restriction that on the number of days. So with this, by adding this layer of M over here, well, these nodes shouldn't. All right, you don't even technically you don't even need those nodes, right? But I'm not sure how nice it would be to just have three edges that are connected to it, so we're gonna be leaving the nodes in for now. Anyways. Right, and what this constraints does is it makes sure that this is effectively day 1, this is day 2, and this is day 3. And by each having an edge weight of m, we make sure that each unit of flow that is going to be leaving S is going to end up being a meeting. By having this constraint that the meeting, if this represents day 1, day 2, and day 3, right, and having the constraint that on this particular day that the number of meetings has to be less than m, this effectively that the number of units of flow that are going through it has to be less than m. That effectively makes it so that the amount of flow is less than m. That by restricting this flow over here, we make sure that the meetings don't go overboard. So, but again, we're still going to be checking in the very end. Yeah, that is all for now. I'm not sure if there's a better way of explaining it, but that's all I got for now. Maybe once I'm more experienced with this, I'll be able to do a better explanation. Now, yeah, and so if those represent the students, and here are the pets. Again, and here is the terminal state. The pets still have that restriction on how many students they want to see in a day. In addition, they have the restriction that within a single day, they cannot meet more than L students. So I swear there's gotta be a better way of doing this, but this makes it so that on a particular day, these 3 again represent the days that no more than L students can meet with the pets. Yeah, and that's about it. That's how we got then that is pretty much equivalent to this graph, just written a little bit nicer. I hope you learned something. I apologize for this is my first video, so I apologize for the rushed nature. I just wanted to get something out into the world, and happy learning.